Welcome to lecture number 5. So, in my previous lecture, I have discussed the solution of the any circuit using network theorem containing the DC sources. Okay. So, now today in this lecture, I will discuss how to solve a circuit problem using network theorem while containing the AC source. So, it may be AC voltage source or it may be the AC current source. So at first, so this is the lecture number 5. So at first simply I will consider a circuit. So like that. So this is a AC voltage source, and with this there is one impedance. Mind it, in case of AC circuit it is called impedance, not the resistance. Okay. So here another thing is it is mainly inductance, but in case of AC circuit this thing is called inductive reactance. Okay. So and here is another current source. So this is a simple circuit. Suppose the value of the voltage source is 5 at an angle 0 degree volt. So as it is a AC quantity, so it contains both the magnitude and the phase angle. This is a vector quantity, and the value of the current source is 2 at an angle 0 degree ampere. Okay, and the value of the impedance is 4 ohm. So now this is called the inductive reactance. Okay, so the value is in ohm. So J5 ohm, and this is called the inductive capacitance, and the value is minus J2 ohm. Okay, all the value are in terms of ohms. So now I have to find the current across this AB terminal, that means through the J5 ohm inductive reactance. Okay, so first I will consider the superposition theorem. So mind it, in case of AC circuit problem, one thing should be clearly mentioned, that the frequency. So here I consider the frequency is equal to 50 Hz. Okay, so now using the superposition theorem, at first I will consider the superposition theorem. Superposition theorem. Okay, so now the procedure of solving the network is similar as the DC network theorem. Okay, the entire procedure is same. So first the step 1, what is our step 1? The step 1 is considering one sources acting at a time. So at first I will consider the voltage source is present and the current source is omitted. That means it is replaced by the open circuit. Okay, so if I redraw the figure, so this is the figure, and this terminal is left open. So now I have to find the current through this terminal. So in our previous problem, the same I have marked it with IL1. Okay, so this is 4 ohm and this is minus J2 ohm, and this is the open circuit terminal. So now what is the value of IL1? Simply the supply voltage by the total impedance occurred. That means 5 at an angle 0 degree divided by total impedance. That means in this mesh actually. So this is J5 ohm. So the total impedance is 4 plus J5, right? So the main thing is in the AC problem is the calculation part. This is very important. So your IL1 will be 5 at an angle 0 divided by, so this is the actually the Cartesian form. Okay, so now I have to convert it with the polar form. So how to convert Cartesian to polar? Simply the polar form is the r theta form. The r is the magnitude, theta is the angle. So this is simply 4 square plus 5 square, and the angle will be tan inverse 5 by 4. This is a simple thing, you have already known it in your engineering mathematics courses. Okay, so I will not go into the deep details, right? So if I calculate it, IL1 will be 5 angle 0 divided by it is 6.40 at an angle 51.34 degree. So further if we simplify it, that means it results 0.781 angle minus 51.34 degree. Okay, so this is the thing, right? So now the second step was the considering the another source. So that means in the second step I will consider the only current source. Okay, so that means if we redraw the figure, so the voltage source is replaced by the short circuit. So this is the short circuited terminal. So it is the inductive reactance, capacitance, and this current is present now. So this is 4 ohm, this is J5 ohm, this is minus J2 ohm. So now I have to find out the current through this J5 ohm inductive reactance. So that is mentioned IL2. So IL2 for the source current 2 at an angle 0 degree. So now what is the procedure? So similar thing, the current flowing from the source to at an angle 0 degree, at that point if we apply KCL, it will divide. So it will divide across these two terminals. So now I have to find the current through the J5 ohm inductive reactance. So now simply current dividing rule is applied here. So your IL2 will be simply the 4 ohm into 2 at an angle 0 degree divided by the total resistance to which the current will divide. That means 4 plus J5, the simple thing, nothing else. So IL2 will be 8 at an angle 0 degree, and if we further solve it, so it will again 6.40 at an angle 51.34 degree. Okay, so further simplifying it, it will show that 1.25 at an angle minus 51.34 degree. Okay, so this is the value of IL2 when the only current source is present. So now the final step is the total current flowing through the marked or AB terminal, that is flowing through the J5 ohm reactance. So when the two sources both are present, that means the voltage source and the current source. So your total current IL will be the summation of IL1 plus IL2. So if we put the value IL1 and IL2, so that means 0.781 at an angle minus 51.34 degree plus 1.25 at an angle minus 51.34 degree. So now these two current are in the polar form. So we cannot add these two current in the polar form. So that in the polar form addition or subtraction is not possible. So we must have to convert the polar form into the Cartesian form, the two currents IL1 and IL2. So what is the procedure? The procedure is very simple, nothing else. The 0.781. So this R angle theta. So the polar form to Cartesian form is R cos theta plus J sin theta. So simply cos of this angle minus 51.34 degree plus J sin minus 51.34 degree, and again for the IL2 1.25, the angle is similar, 51.34 degree plus J sin minus 51.34 degree. So your IL will be, after converting this, so your IL will be, for the IL1, if we simply multiply the value with 0.781, it will show that 0.487 minus J 0.069 for the IL1, and for IL2 it is 0.78 minus J 0.975. Okay, so now we can add this two value IL1 and IL2 because it is now in Cartesian form. Okay, so if we add this, the IL will be, simply we have to add the real part with the real part. So that is, this is the real part, okay, and the term associated with the J, so this is the imaginary part. Okay, so now I have to add the real part with the real part, so it is 1.268, and now the imaginary part becomes J 1.585. Okay, so this is in ampere. So again, if you want to convert it into the again the polar form, so it will simply the conversion from Cartesian to polar, so that is the magnitude will be square root 1.268 square plus 1.585 square, and angle will be that simply tan inverse b by a. Okay, so this will 2.03 at an angle minus 51.34 degree ampere. Okay, the simple thing, if the Cartesian form is a plus ib, so if I want to convert it into the polar form, so magnitude r will be square root a square plus b square, and the angle will be tan inverse b by a. So the simple thing is there, nothing complicated. Okay, so this is the procedure of solving any network using superposition theorem containing the AC sources. Now if I consider the same problem using the Norton's theorem, so how can I solve this? So again I am redraw the circuit, the original circuit. Okay, so this is the original circuit. Okay, so the value is 5 at an angle 0 degree volt, 2 at an angle 0 degree ampere. So this is 4 ohm the impedance, and this is J5 ohm inductive reactance, and this is minus J2 ohm inductive capacitance. So now if we apply Norton's theorem, okay, if we apply Norton's theorem, so the step was the similar. So first step will be the I have to find the short circuit current across this terminal, that means through which terminal I have to find the current. So first this terminal is replaced by the short circuit. So the figure will be very simple, just short circuited this path and the remaining components are same as it is, and through this short circuit part the current is flowing, that is known as I short circuit. Okay, so now if I want to find the short circuit current, that is basically, suppose this is a voltage source 5 at an angle 0 degree volt. From this voltage source one current is flowing, suppose this is I1, and another current source 2 at an angle 0 degree, suppose this current is I2. So the two current, it is flowing through this path and it is flowing through this path. So that means at this terminal the two current entering in this short circuit path, that means the summation of the two current I1 and I2 entering in this short circuit terminal. Okay, so your short circuit current, it will be the summation of I1 plus I2. So what is your I1? What is your I1? Your I1 will be simply, so this is the 4 ohm, I1 will be simply voltage by impedance, so that means 5 at an angle 0, and this is the simply impedance 4 ohm, that means the angle is 4 at an angle 0 degree. So look, the interesting thing is, if the component is, that means the passive element is inductive reactance, so the angle is plus 90 degree, and if the component is inductive capacitance, the angle will be minus 90 degree. It's a simple thing. But if the element is a pure resistance, the angle will be 0 degree. Okay, so here the 4 ohm, the pure resistance, so it is 4 at an angle 0 degree. So and the I2 is similarly the, that means here is actually the current source. That means the simply this current is flowing through the short circuit terminal. So this is simply 2 at an angle 0 ampere. Okay, so this is in ampere, right? So again, if further simplify the solution, then it will be 5 by 4, that means 1.25. So now this is actually we divide the two polar form. So to divide the polar form, we have to divide the real part, that means 5 divided by 4. Actually there is a division part will be taken in between two real part, and in between the two angle there will be subtraction. Okay, this is the rule. In case of multiplication, the rule is real part into real part, and the angle of the angle are additive in nature. But in case of divide, the real part, the two real part will divide and the angles will be subtracted. Then 5 by 4, and here the two angle are 0 degree. So if we subtract 0 minus 0, it will again 0. So this is irrelevant here. Okay, so that means 1.25 at an angle 0 degree plus 2 at an angle 0 degree. So the total current, that means 3.25 at an angle 0 degree, right? So now the second step is to find the Zn, that means Norton's equivalent impedance, not the resistance. I staged the word. In case of AC circuit, this is called impedance. So to find the Zn, what will be the circuit? The circuit is the voltage source is replaced by the short circuit and the current source is replaced by the open circuit. The similar thing, and the this short circuited terminal is replaced by the open circuit. Okay, so that means if I redraw the figure, that means this terminal is short circuit and this load terminal is open circuit, and this terminal is also open circuit as it is a current source. So now I have to find the Zn looking from this terminal. Okay, this is the 4 ohm and this is minus J2 ohm. So now what is the procedure? Just consider a imaginary, that is a fictitious voltage source in this open circuit terminal, and from this the current is flowing. Okay, that is one current is flowing in the left side and another current is flowing in the right side. As the right side is open circuit, so no current is flowing to the right side, so only one passive element is present here, that is the 4 ohm. So that means the Zn is simply the 4 ohm. It is very easy to calculate the Zn in this particular circuit. Zn is actually the 4 ohm. So now the third step, that means the final step, is to form the Norton's equivalent circuit. So that is simply, so this is the current source, that is actually the ISC. So now the current source is actually the AC current source, right? So AC current source, and with this is actually the Zn, and with this is actually ZL. Okay, this is Zn and this is ZL. Now I have to find the current through this ZL, that is the load impedance. Okay, so now the formula will be IL equal to ISC into Zn divided by Zn plus ZL. Okay, simply the current is will divide across this terminal. So now using the current divider rule, the formula is already established. So the IL will be ISC 3.25 at an angle 0 degree, and what is the Zn? That is 4 at an angle 0 degree, the impedance part, and by total impedance, that means 4 angle 0 degree plus ZL, the load impedance. The load impedance actually here the J5 ohm. J5 ohm is the inductive reactance. So what is the impedance? I have previously mentioned the inductive reactance. In case of inductive reactance, the angle should be plus 90, and in case of inductive capacitance, the angle should be minus 90. So it is J5 ohm. So that means the value will be 5 at an angle 90 degree. Okay. Suppose this was the inductive capacitance minus J5. So in that case, the value will be 5 at an angle minus 90 degree. Okay. So this is the common thing. So now if I calculate the IL, so very simple thing. That means I can multiply the numerator because these two terms are in the polar form. So your IL is simply 3.25 and 4. These two real part I can multiply. That means it is 30, and the angle between the two component we add it. That means 0 degree plus 0 degree. So it is exactly irrelevant. So now the denominator part, it is in polar form. So we cannot add the two polar terminal. Okay. So again I have to convert it into the Cartesian form. So now the Cartesian conversion will be 4 plus J5, nothing else. Very simple thing. So again 4 plus J5 if I can convert, if I add the two terms 4 plus J 4 at an angle 0 degree plus 5 at an angle 90 degree. So it is, I have already calculated in the first problem 4 plus J5. If I go back to the first problem, the 4 plus J5. So if I convert it into the polar form, it is the result will be here 6.40 at an angle 51.34. Yes. So simply put the value, that is 6.40 at an angle 51.34 degree, and it is exactly the angle 0 degree, nothing else. So your IL will be, again you divide the two real part, that means 13 by 6.40. So it will show 2.03, and the angle are subtracted, that means 0 minus 51.34. So it is minus 51.34. So now again it is proof that the load current, the value of the load current is same using superposition theorem or using the Norton's theorem, because in Norton's theorem it is showing 2.03 at an angle minus 51.34 degree, and using the superposition theorem it is also showing 2.03 at an angle minus 51.34 degree. So like that. So these are the two network theorem using AC voltage sources. So now again if I check the circuit using a simulation, say to verify the result are same or not. Okay, so let's go to the simulation part. So now this is the circuit I have already connected in the simulation platform. So this is the AC voltage source, that is mentioned is 5 at an angle 0 degree. So now here is the parameter is the peak amplitude. So 5 is the RMS value. So its peak value is 5 into root 2. Simply the RMS to peak conversion, and the phase angle is 0 degree, and the supply frequency is 50 Hz. Okay. And again this is the AC current source that is given 2 at an angle 0 degree. Again the 2 value is the RMS. So its peak value is 2 into root 2, the 0 degree phase angle and the frequency 50 Hz. So it is actually simple thing. But here is actually the pure resistance, the impedance, actually the value of R is equal to 4 ohm. Up to this it is okay, right? But the interesting thing is that to calculate the value of L and C, because in our theoretical problem the value of inductive reactance is J5 in ohm. Okay, but in simulation I have to put the value of only the inductance, that is in Henry, not in ohm, not the value of inductive reactance. I cannot put the value. So we have to convert the value inductive reactance to the only inductance. So the very from our basic electrical knowledge, XL, the inductive reactance, can be written as XL equal to omega L. So where omega is the angular natural frequency, that is equal to 2 pi into f, where f is the supply frequency, that is mentioned 50 Hertz. So that means 100 pi omega. So omega L equal to given is 5 in ohm. So L equal to 5 by omega. So omega equal to 100 pi. So that is L is equal to 5 by 100 pi. The simple thing is mentioned in this part. Okay. So now if I open the value of L, it is showing 5 by 100 pi. That is in terms of Henry, right? The same thing is applicable for the inductive capacitance. Inductive capacitance is written as Xc, that is equal to 1 by omega c. So in our problem it is given as 2 J2 ohm. So now I want to convert it into the value of only capacitance, that is in terms of farad. So now I have to put the value of C. So 1 by omega c, that is equal to given 2. So C equal to 1 by 2 is omega. So omega is again 100 pi for the 50 Hz supply frequency. So C equal to 1 by 200 pi. So now set the value of C, that is 1 by 200 pi. It is in farad, right? So now the current flowing through this inductive reactance is the AC current. So it contains both the magnitude and the angle. So this, from this turn point, the peak current is showing, that is the peak amplitude. So but in our calculation all the current are in RMS. Okay, so from peak to RMS conversion, that is peak by root 2, that is equal to RMS. Simply this is a gain factor of 1 by root 2 to convert the peak value into the RMS value, and from this point we can show the magnitude of the current. So now if I run the simulation, so it is showing the magnitude of the RMS value of current is 2.03 ampere, while the phase angle is minus 51.34 degree. So it is actually the exactly same when I solve the circuit in theoretically or in mathematically, right? So the conclusion is irrespective of any network theorem, if I solve the circuit in theoretically or in MATLAB or Simulink platform, the result is exactly same. So that is the thing, that is the key point. Okay, so nothing else. So this is the today's lecture of solving any network problem using the network theory, AC network problem with AC voltage source or AC current source using superposition theorem and Norton's theorem. In my next lecture, I will discuss the similar problem using the Thevenin's theorem and maximum power transfer theorem. Okay, so this is for the today's lecture.